In the last class, I introduced liquid phase sintering in brief. I intend to continue with it to discuss liquid phase sintering because that is the process which gives us lots of commercial products. The silicon nitride bearings which I had shown earlier were based on liquid phase sintering, I have told you. Ferrite cores, capacitors, all of them are fabricated using liquid phase sintering. The materials are liquid phase sintered first and then the grain boundary is engineered. So, I wish to devote some time more for today's lecture to discuss liquid phase sintering. But before I come to it, let us consider the dynamics of what drives sintering. In sintering, let us take the solid phase sintering first, which I have drawn over here. The driving force is a reduction of surface energy. Smaller particles are there, they have high surface energy. So, if they agglomerate, what will happen? It will generate a larger particle, surface energy will be reduced. So, if I look at this diagram for solid state sintering, I have a grain boundary here, this is a grain and this is a grain. This is the grain boundary energy. And here what I have drawn is the energy due to surface and vapor. This grain, surface and vapor, and this theta is the equilibrium dihedral angle. This dihedral angle plays a huge role in determining sintering, and it is dealt with very extensively, as I said, in the book by Barsoom. You should look at the mathematical calculations over there. Whereas this is the state in solid state sintering, I have grain boundary energy and solid vapor. In liquid phase sintering, what we are faced with is much more complex situation. This is a grain, this is a grain, the liquid has been generated over here. So, here we have got the grain boundary surface energy. Now, the surface vapor which was there in the solid state is replaced by the surface liquid free energy, and this is the dihedral angle. But how things get complicated is given over here. Is, as you know, as you have seen in many places, some surfaces get wet, so the water droplets spread out. Some surfaces do not allow water droplets to collect, and we have two types of surfaces generated. This is a non-wetting surface where the water droplets form a sphere, and this is a wetting surface where the water droplets spread out. Now, here what we have now is we had surface solid liquid free energy, I had stated over here. On any grain, this solid is the grain, this solid is the grain, and this is the liquid that is forming. This solid is the grain and the liquid is forming over here. We still have the gamma SL, solid liquid energy, but again we have the solid vapor also. In addition, we have the liquid vapor. Similarly, over here what we have is the SL, solid liquid free energy, is there, but now we have the solid vapor over here also and the liquid vapor over here also. So, in contradistinction to the here what you have is the solid state sintering, and here you have the liquid state sintering. You can see there are more free energies which are coming into play, like liquid vapor free energy over here which has come in, and I have drawn a relationship where we can state that, let us say this simple equation, gamma SV is gamma SL plus gamma LV cos theta. This theta is the dihedral angle. So, the surface vapor free energy is a summation of this. The smaller the theta, what will happen? Liquid will spread. The higher the theta as it is over here, the liquid will form droplets. So, essentially if I rewrite it, high surface vapor and low surface liquid free energy promote wetting, simply from the value of cos theta. For liquid phase sintering, this dihedral angle is always between 0 degree and pi by 2. This is an essential factor for ensuring liquid phase sintering. What happens if what we have is a system where the surface energy concentration is such that the liquid does not wet the surface, it forms a globule. What happens over there is that if the system is non-wetting, then the liquid will form beads, they will collect at places, and in that case, which I have written over here, so what happens, this is a surface, this is another surface, and the liquid has formed beads like this. How does sintering proceed? In that case, sintering can only proceed even in the presence of liquid phase through solid state route. Once the liquid generated is not wetting, liquid phase sintering will not occur. There are other aspects of this wetting and non-wetting behavior. Let me take this particular diagram. The first one is a case where the liquid wets the surface. So, all of you have, if you just pull your two hands, if you wet your hands, just pull them to a bit, you will see there is a small capillary generated between the fingers, because the water has wetted my fingers, and as I try to pull them, I will see a liquid film forming between the two fingers, which is exactly what I have shown over here. What I have said, this is a solid grain, this is a solid grain, the liquid wets it. In that case, the contact angle, the wetting angle is less than 90 degree, and in this case liquid spreads. So, as sintering proceeds, the surface gets more and more wet. What is the consequence of that? The consequence is simply this, that if the liquid is wetting the grains, they are pulling the grains also closer. Like say you have got dry sand, it occupies a certain volume, you pour water on it, the sands pack. Why? Because the sand surface has been wetted by water, the surface tension of the water is pulling the grains together, and this is exactly what happens due to capillary process in for surfaces that are wetted. However, there is one condition also where the contact angle is 90 degree. Rare, happens. Most of the cases are liquid has wet the surface, the grains have been pulled together, like I said, you wet dry sand, they pack, and if they are packed more, sintering will proceed faster. In another case, let us presume the contact angle is 90 degree. If you look at the energetics, you will find that there is still a net attractive force, and liquid phase sintering will happen, though the amount of energy available for this is lesser than this. Now comes the case where beading occurs. I talked of this. The liquid does not wet the surfaces. I had said the liquids form a bead. So, as more and more liquids are generated, the particles get pushed out. And in this case, sintering through liquid phase is not possible. So, if I am looking for liquid phase sintering, I have to first look for the capillary forces. Does the surface wet it? Is this angle less than 90 degree, the contact angle? Ideal. That will help liquid phase sintering. Even if it is 90 degree, it will work. But the liquid phase has to wet, otherwise the grains will get pushed out. Now, when I am doing liquid phase sintering, what is fundamentally happening? Fundamentally, what is happening is this. Let's redraw the diagram. I have drawn this diagram many times. Let me say this is one grain, this is another grain, this is a third grain, this is a fourth grain. Let me stick to 4 grains. This is a system of, say, your porcelain cup, which is made from feldspar, flint, kaolin and clay. Let me, for very simplicity's sake, presume that this is the feldspar. This is the feldspar. So, as a very first step, this feldspar will melt. As the feldspar melts, this particular grain, it starts wetting the surfaces over here. It will wet this surface, it will wet this surface over here. What happens next? Now, I don't think I am that good an artist to have exactly the same size of the diagram I had drawn, though I will strive. Okay, it looks almost similar. I have got the feldspar forming a low melting liquid. It is spreading over here, it is spreading over here. Now, if I blow this part up, I look at this under high magnification. What will happen? This is this grain and this is this grain. So, the liquid here will penetrate this area between the grains. If it penetrates, if it wets, then what it will do? It will start pulling the particles together. It is true in this particular case, the next diagram should be this grain, let me say A, B, C, or no, this is 1, this is 2 and this is 3, fine. These grains are getting smaller. Why? Because the liquid is reacting and dissolving the grains, and the grains are getting smaller. So, during this particular period, what is happening is that liquid is penetrating into the grain boundary, and for liquid to penetrate into the grain boundary, where I showed for good liquid phase sintering a layer has to develop. Now do not think it is a, if I look at this measurement with a scale, it is 1 centimeter. Sorry, in real life this is less than a micrometer. It is only that I have drawn it to a large scale. So this micrometer thick liquid layer is formed, and for this the grain boundary energy is gamma, twice the gamma SL, which I can get from over here, as the equilibrium dihedral angle is 0. The mechanism of the liquid phase sintering. So I have already said the liquid has to penetrate the grains on wetting, the particles have to be pulled together. Now you see, I had drawn this diagram here and had given you a brief hint that look, the particles, the feldspar melts, it forms a low melting liquid, it migrates to the alumina grains, to the silica grains, to the kaolin. This feldspathic melt reacts with them, forming a liquid phase which is now richer in silica and alumina. And as I showed over here, each of these silica, clay grains, they are getting smaller and smaller, because the liquid is forming as the original feldspathic melt had reacted. What does this allow? What it allows is, now because the liquid has wet the surfaces, it is pulling the particles together, but before that, as I have just now said, it is also dissolving the solid. Which part of solid? Let me assure, let me draw a grain which is, it is a deliberately drawn diagram. Let us assume this is a grain and there is liquid all around it. The part that will dissolve fastest is this one, because at this point with the sharp corner the surface free energy is the highest. So what will happen? The liquid will react with it, the sharp edges will be removed. Second, maybe this will be made rounder. So what happens is, A, the liquid forces a capillary action. Second, it sort of rounds off the grains, and third, the liquid also has a lubricating action, and hence the packing of particles during sintering occurs, sintering the liquid phase. This is the advantage of liquid phase sintering. In solid state sintering, where there is no liquid phase generated, this particle rearrangement of the liquid phase is not possible. Secondly, the liquid, as I had said, under good conditions of liquid phase sintering, it will flow and fill up all the pores. I have shown you in the solid state, pores are a problem because they have to be eliminated. I will come back to it anyway. So here the liquid forces a rearrangement due to capillary action on account, and also particle rearrangement as the rough surface of the grains get rounded off and the liquid itself acts as a lubricating agent. So the very first phase of liquid phase sintering is this A, particle rearrangement and completely filling up of pores. In fact, this is where the maximum densification takes place. If I Uh, Let me presume I take sand. It doesn't depend whatever sand you have, and I try to compact it. Uh, all of you have read in your material science course that the most packed system is uh, face-centered cubic lattice, and with an atomic packing factor of 0.74. This is true geometrically. Now, obviously, you have to understand that when I am taking sand, it has got particles of different grain sizes, and so this packing is not achievable. What I may land up with is this is if I compact, and you can see there are a lot of pores. Normally, if I have taken a ceramic powder and I have compacted it in a die, even under the best of the conditions, I do not expect more than 60% packing. That is 40% of the space will be pores. That is, I have taken the ceramic powder, I have pressed it into the form of a pellet, and now I am looking at the porosity. 30 to 40% porosity will be there. So, now let us assume that we have taken this pellet, green pellet, that is not fired, with, say, let me pick up a figure, 30% porosity. You see, when I talked to the last day, I will come to it again. During solid phase sintering, these pores have to close, and closure of the pores is a major problem. I will come back to this point later. But in liquid phase sintering, what is the advantage we have? Even if we have 30% porosity, liquid will fill all the pores. So, essentially, pore removal, if I have got proper liquid phase which is properly wetting and sufficient amount, that is not a problem. The maximum densification occurs in this first stage itself, this A, due to particle rearrangement and the liquid completely filling the pores. In the next stage, what we have is now what I had drawn earlier is a variation of what I had drawn earlier is, let us presume liquid has been formed, and let me draw 4 grains. The way I have drawn it, you can see this grain is in contact with this grain over here. Let me level 1, 2, 3. These 2 grains are in contact over here, but over here this place has the liquid. This is filled with the liquid. From your high school chemistry, you know that the very existence of a contact here and the lack of contact here and here will lead to a chemical potential difference between these 2 points. That is, the chemical potential difference, there will be a difference in chemical potential between this point and these 2 areas. And what will it lead to? So, it will lead to more dissolution. So, dissolution will start over here. That is, again I have to pardon my lack of drawing skills. So that now, so that now the liquid phase fills it, and thus reduces the difference in chemical potential. The next thing that happens is the grains were in contact, the contact area is dissolved, the liquid has penetrated into the region between the grains, and here, you know, in liquids diffusion will occur. Wherever there is a concentrated number solution, it will diffuse away into areas which are less concentrated, meaning you have a feldspathic liquid, you have an area where it is richer in alumina, richer in silica. So the areas richer in silica or alumina will force diffusion of silica and alumina into the less rich areas, and they will be moving away. At this particular stage, the liquid is doing two things. The liquid has been formed, this sort of a thing has occurred. The capillary pressure now, due to the capillary pressure, these grains whose surfaces have been rounded off, they are pulled closer together due to the capillary effect. Oops, this should be a round one. Due to the capillary effect, and at this particular place what happens is reprecipitation occurs. I have written it in a single word which is not fully conveying the meaning. I have written this: reprecipitation away from contact area. Why? What I meant to say in full language is the liquid will dissolve the sharp edges, will dissolve the contact areas, so that these areas become rich in whatever is there in 1 and 3, and they will diffuse out to this area which is less lean. And over there again, as this liquid gets richer in 1 and 3, they will start reprecipitating. That is what I have talked of, reprecipitating from the contact area, which leads to shrinkage and densification. Now you have to understand that in liquid phase, shrinkage and densification is much more faster than in solid state sintering. Is much more faster than in solid state sintering. Why? Simply because the diffusivities of the ions are much more than in solid state, and diffusion is occurring from the alumina or silica rich areas. In the present case, they are diffusing out very fast, and as the diffusivity in liquid is higher than in solids, sintering occurs much more faster. Over here, however, there is a flip side to this also. If reprecipitation does not occur, what can happen is the grains may get coarser. I have conveniently drawn over here that this grain has become smaller as the surface has been eaten away by the liquid, and then reprecipitation occurs. Yes, the liquid has eaten away the sharp edges, a liquid has been generated, but then the thermodynamics is such that each of the grains get bigger. This is the flip side of liquid phase sintering which one has to consider. And what happens is, if you have got very fine grains to start with after pressing, if the liquid phase generates coarse grains, you will have a body with much larger coarser grains, the fine grains are gone, with thick liquid phases. This coarsening is undesirable frequently in liquid phase sintering. Anyway, this is the flip side. So, what we have over here is this mechanism in liquid phase sintering, particle rearrangement, liquid completely filling the pores, solution reprecipitation, which I have said over here. Now, here is a graph that I have drawn which talks of liquid phase sintering mechanism. This is a log scale and this is the shrinkage. As I had said earlier, during the particle rearrangement phase itself, densification occurs. And this is exactly shown over here. This is the stage of particle rearrangement whence the large shrinkage occurs. I had talked of the liquid eating the grains, preparing a solution, and the solute being reprecipitated elsewhere. This is the solution reprecipitation zone. After that, what happens is this. If I draw on a large scale, and I had also stated earlier in my lecture yesterday the very large end. Let me draw on a very expanded scale 3 grains. This is grain 1, grain 2, grain 3. This is the liquid. Due to solution reprecipitation, these dendritic crystals have been generated. These are what? These are the solution reprecipitated material. At this stage, what happens is all these dendritic structures, they keep overlapping with each other. These are all precipitations from the supersaturated solution. So, you will see that what is happening is that these dendritic structures are getting interlocked, and then the last step happens. This is the skeletal sintering. So, in this particular case, we have a skeleton. This is grain 1, grain 2, grain 3, liquid phase with skeletons of reprecipitated material, and these reprecipitated grains which are dendritic in nature, which interlock, they sinter. Leading to very high densification. You have to remember the X scale is in log time. The case that I have taken up here, 50% of the densification had occurred with the first 2 minutes of sintering. The rest of it occurred over the rest of the 98 minutes of sintering. So, for liquid densification, the liquid sintered process, liquid phase sintering, it should be, we need liquid phase wetting of the solid surface, surface amount of liquid, sufficient amount of liquid should be there to wet all the surfaces. The solubility of the solid in liquid has to be high. Finer the grains, the higher is the capillary pressure. I had told you why. And as the capillary pressures are higher, the densification rates shall also be higher. Now, if I may come back to this diagram, here I have got the grains. This is the skeleton. Let us presume it has sintered and sintered well. We still have plenty of liquid phase over here. Plenty of liquid phase over here. Does this liquid phase pose any problem? Well, yes, very clearly yes, because A, if there is liquid phase, amorphous, creep resistance will be slow, electrical properties will be detrimental, and finally the mechanical behavior of the amorphous liquid phase which is present within the skeletal network will lead to easier fracture and also decrease the maximum surface temperature. The silicon nitride bearings that I had shown, what was done there is the silicon nitride grains were sintered, the skeletal structure was developed, the liquid phase was there, but this liquid phase, which would have been amorphous otherwise, was forced to undergo crystallization. In that case, if I have got a liquid phase which can be crystallized, I have got what I need finally. So, the silicon nitride ceramic bearings which you had seen was entirely liquid phase sintered, with grain boundary engineering being resorted to for converting the glassy phase into crystalline. A lot of ferrite cores are used, most of you know, in transformers. They need to be very dense, they need to be fine grained, and they need to have uniform properties. And all these ferrite cores are sintered by liquid phase sintering. However, if the liquid phase converts to an amorphous phase in the ferrite core, it would be detrimental to its use. The ferrite core would heat up and then crack. So, there also the liquid phase was engineered so that it converts to a solid phase. There are many of similar examples, for example, in capacitors, ceramic capacitors. Because ceramics have got high dielectric constants, so the amount of size, shape of the material can be thinner than the ones made from polymers or paper. In many cases where we believe that solid state sintering has occurred, subsequent results have shown that it was a liquid phase which had formed and then crystallized. So, yes, solid state sintering is a way out, but in most of the industrial applications, especially for mechanical applications, liquid phase sintering is the preferred way out. Now, here is an issue again which concerns how do these grain boundaries move? It can be in the solid state, it can be in the liquid state. Because in, let me go back to that silicon nitride ball bearing which you had seen. It is just not sufficient that the amorphous zone between the grains be ceramized, but it is also important that the particle sizes remain uniform to the extent it can be done. That is, there should not be large scale variation in particle sizes, as that would make the properties dependent totally on the microstructure of each bearing or maybe areas of the bearing. So, whether you are doing solid state sintering or liquid state sintering, you have to talk of grain boundary mobility. The very first thing, something that most of you know and it may be a useless recap, is let us assume two grains. This is a grain boundary. This is a concave surface from this side, convex surface from this side, concave surface from this side. You see a vacancy right out here. The only way this vacancy can move, that is, if you are heating a material, the vacancy will move. In which direction will it move? This will move to this direction. And the grain boundary shall move left to right. So, the vacancy in this particular diagram moves from right to left, because, very simply because, if this vacancy has moved, how would it look like? This, but a packing, and this would become a vacant spot. So, the vacancy moves from right to left and the grain boundary moves from left to right. Why do I bring this up? I bring this up is because we now need to know what sort of grains grow in a ceramic process. We may have just a triangular grain which has three sides. We may have a tetrahedral grain which has got four sides. So, 3 sides, 4 sides, 5 sides, 6 sides will be there, depending on how things fracture, how the powders are produced. When we have packed them in a die and we are heating it, I brought this up to explain how grain boundary moves. What we see always is grains which have less than 4 sides, they collapse. And this you can see in this diagram. Why? This one has 3-sided grains. Look at the nature of the curve and what I had drawn here. The only thermodynamic way is for this grain to get smaller and smaller, while these grains get larger and larger. So, grains which are less than 4 sides will become smaller and smaller and collapse. Grains which are 6-sided, they have got flat grain boundaries, no curvature, they are stable. So, grains with 6, maybe 5, at times 4 depending on the size, they are stable. And grains which have got much larger than 6 sides, look at this particular grain. The curvature is such that this grain will keep growing. It these will be pulled apart, all these smaller grains get eaten up, and this grain grows to a very large size. As a result, if I am just taking this particular case, I will have a mixture of microstructure. This grain is stable, this grain is stable, this grain is stable, all others they vanish, and I get very, very large grains. And hence, we have a microstructure which has stable 4-sided, 5-sided, even 6-sided grains, and there are huge grains. This sort of a microstructure which has excessive grain growth, that is, some grains have grown very large, are not mechanically stable. The question comes that when we are sintering anything, we have applied pressure to make it form a die, there are internal pressures, it is being heated at a temperature, we can control the temperature, rest of the things we cannot control. How do we stop this large scale grain growth? So let us look at grain boundary mobility. I have already talked of intrinsic grain boundary in the previous slide. One way of decreasing grain boundary mobility is through an extrinsic process. We can have a solute which dissolves at a very slow rate. Let us presume that in this diagram, as I said, this grain will grow very huge. But let us presume in this diagram we had solutes at the grain boundaries. What would happen? These solutes would take time to dissolve. That would pin the grain boundary over here, and very large scale grain growth of the grain boundary would be defeated. As a result, if there are solutes present in the grain boundary mobility can be decreased. The third one I have written is again a variation of the same statement, except that I have an inclusion which does not dissolve, it just stays there. And what would happen? If the inclusions are large ones and they are in large volume fractions, they would limit the grain growth. The last one I have written is material transfer across grain boundary. That is, when I am sintering silicon nitride, silicon and oxygen has to interdiffuse. So, depending on this material transfer, we can control the grain boundary mobility. Why am I bothered? You see, I am talking about grain boundary, but whether it is whatever sintering you are doing, at the very first stage you do have pores. In solid state sintering, pores can shrink. In liquid state sintering, pores can get filled. But again, if I take solid state sintering case only, these pores can also get very large. There is Oswald ripening. But means gases come from different areas, increase the volume of the gases inside the pore size increases. This gas inclusion in the pore can also happen due to reactive gas evolution. At times, we do resort to reactive sintering, and at that time gases are evolved, and these can come and collect in the pores, increase the size of the pores. Sample bloating, this is a major problem. There are many clays which swell up when they are heated. It is true that today we have learned how to make use of that bloating to increase the engineering properties. But sample bloating also can happen, which can lead to coarsening of pores. Now, what happens if the pores don't shrink, pores get larger? If the grain boundary mobility is higher than in pores, than the mobility of the pores, the grain boundary will move faster than the pore, and as a result, we will land up with a grain. The grain boundary has moved out, the pores are stuck within this grain, and these are closed pores. So, if I intend to summarize what I covered today, my learning objectives were that liquid phase sintering is rapid. These are the learning objectives. It results in uniform densification. I discussed the surface energy, the capillary forces, how they affect the sintering rate. I have discussed the sintering mechanisms, particle rearrangement, solution reprecipitation, and the solid state skeletal sintering. The factors that really have to be considered over here is during the liquid phase sintering, the liquid phase which would have otherwise formed an amorphous phase might require to be engineered to form a crystalline phase, so that the mechanical properties, the creep resistance, the electrical properties are within the limits of what we need. I'll stop here, but before stopping, let me say this. In the next class, what I should be taking up is review of the factors that affect solid state sintering. What are the different factors, and take it free from there to complete the sintering chapter. Thank you.